I will give 1 minute kind reminder by standing up here to the presenters. So our first presentation is Health Q, unveiling the question compatibility of the LLM chains in healthcare conversation. Let's welcome. Thank you.
Hello, my name is Holly. I'm from Columbia University. My co-first author, Ziyu Wang, is from University of California, Irvine. We are honored to present to you the health skill unveiling questioning capability of LLM chains in healthcare conversations. So the motivating example is that a patient comes to the hospital, but the patient doesn't come to the hospital with a large chunk of complete description of a disease. For example, my complaint is I hurt my foot during the hospital visit. In the traditional case, I'm handed multiple lengthy forms to complete. The form asks a lot of questions: do you drink, do you smoke, etc. At one time, I even had the X-ray finished before I could complete the form, and the form asks numerous questions, and some of them are relevant, some of them are irrelevant, but it missed some very relevant question that a chatbot would ask you. So. But the core problem is that most of the benchmark in LM or in chatbots focuses on question answering, so QA dataset. You can see a lot of QA benchmark, but now we need to design some other things that prepares the query or question. So this is how we came up with the idea that how good are healthcare applications in the LLM's era at asking relevant questions based on a short complaint. But the difficulty is how do you get the data? To evaluate how good a question is difficult because we don't have the data of questions of a complaint. So we came up with the idea to let LLM recover other information, recover all the information that's relevant to a disease, given partial information. And here's our framework. So the framework is that first we have some health conversation data set. Some of the data are used for vector, the knowledge base for the LM chains, and some other data are used for evaluation. This is similar to the train test split because we cannot leak the information if we want to use some of the information for testing. And the two components in the middle are, on the top is the LM healthcare chain. Nowadays, some paper call it agentic system, or but at the time of last year, we just call it LM chain applications, which act as the chatbot to mimic the reception or the nurse or the doctor. On the bottom, this is the virtual patient simulator. Nowadays, people call it LLM for role playing, but at that time of our experiment, it was not a widely popular concept. So the virtual question, the virtual question prepares a question to the LLM healthcare chain, which is shorter than the full text, and the LLM chain, based on that short question, prepares the next question to ask the patient, and that question is evaluated in two ways. First, by LLM judge by interrogation. So another LLM with the knowledge of the ground truth compares the question to the ground truth and see how relevant it is. And second, we can also use that simulated patient again to let the simulated patient answer that question that the LLM chain asked, the healthcare chain asked, and then we evaluate whether that induced answer retrieve more information from all the patient knowledge. So we evaluated many of the SOTA chains at that time, where we first built a rule-based, hard-coded workflow based just on retrieval without the LLM as a baseline. This mimics the rule-based chat box in the traditional way. And then we have the RAG, which is a retrieval augmented generation, which is basically you do a vector search in the data, and then you use the top K candidates in the LLM to create answer, and then we can add a reflection module to let the LLM rephrase the RAG result, and then if we can do the reflection and do retrieval multiple times, we can do it step by step. For example, if the first retrieval is not that good, you could do it another retrieval, and then if you do the multi-shot, you can have the reflection plus chain of thought. And adding to that, if suppose you can get some answer consistently, there's an idea of chain of thought consistency, which is that you could add a little bit of noise to that chain of thought system, and if you can, and you run it multiple times. If you run it multiple times, it reaches a similar conclusion, and you could pick the consistent conclusion to the result. And finally, we have the React, which is the very first reason acting agent. And we use the both summarization based evaluation and LLM judge interrogation for the evaluation, because the summarization based evaluation are closer to the traditional NLP standard. Includes ROG, which is like n-gram based evaluation, and also the set comparison from the NERs. So in this case, entities are medications and symptoms, etc. And the LLM judge is sometimes sensitive to the prompt. This is why we use the different prompt, for example, relevance, usefulness, specificity, and we tested different prompt against the system. And the dataset is the chat doctor dataset and the MTS dialogue dataset, which are healthcare conversations. And we extracted 796 patient-doctor statement pairs. So to illustrate a little bit further, in a conversation, some of them are what is known by the patient, but there are some other things that only the doctor knows. For example, the treatment of the disease or the medical term of the disease. Because if I come to the doctor, I said I hurt my foot, I can't say I have a closed fracture of a fifth metatarsal bone. This should be something that's known to the doctor, not to the patient. And we clean the data, and we set up. We use the open source models in the healthcare chains to mimic the situation that it needs a locally hosted system for small clinics or hospital to have privacy, but we use the better, like a more complicated model for judging. Let's see. The result is first, we can see this is the normalized mutual information matrix for the bin data. So each chain has a score, and we could see that there's there's a lot of correlation between the interrogation-based judgment and the summary-based judgment. And interestingly, that in this case, the LLM judge isn't quite sensitive to the prompt. So you could see a lot of high scores on the top left, but fluency is a less relevant prompt to usefulness, and this is expected behavior. And you could see on the bottom left corner, there's some mutual information between the LLM as a judge criteria and the summarization-based criteria, which shows that it's consistent with both field. And algorithms that generally performs well on general purpose tasks. For example, the rag and the rag with reflection and the chain of thought self-consistency generally do score better than the hard-coded traditional way. So using a LM is in the retrieval system is better than not using that in this conclusion. But but interestingly, the React agent, when not a lot of tools are provided, doesn't have an advantage than compared to the vanilla retriever augmented generation, and we think it is due to the problem that we only have we have one we don't have a lot of tools provided to the React, and this isn't some retrieval test that needs multiple tools. So in this case, directly putting that knowledge base into the hard-coded, well, not the hard-coded, directly putting that retrieval part into the retrieval augmented generation workflow is sufficient. And I thank you for your attention. Yeah.
Okay, thank you very much for the presentation. Our next presenter are, for the presentation, electrometer, the practical electrolyte measure system. Thank you. Yeah.
Hello everyone, my name is Johnny, and today I'll be presenting my group's research, Electrometer, the practical electrolyte measurement system. So this is a collaboration between William & Mary in Virginia and Jamestown High School. Electrolytes affect our health, and the depletion of them really has negative consequences. Electrolytes are present in everyday objects we eat, like bananas, and they're also prevalent in sports drinks or juices. But they play an important role since they help us maintain our health. Things like regular heartbeat, blood pressure, concentration, focus, alertness are all things that electrolytes have a vital role in playing. The depletion of electrolytes has negative consequences. Some are life-threatening and some are just performance affecting. So an alarming statistic is that in 2021, 700,000 people died from the worst symptom of electrolyte depletion and other things. But electrolytes help maintain blood pressure, and so 700,000 people died from hypertension. Nearly half the US population has hypertension, and out of that half, only a quarter have their condition under control. And electrolytes really could help them, but it's really hard to know how well you're replenishing your electrolytes. Some additional symptoms include weakness. Your muscles don't function as well when you're working out. When you're walking around, you might have increased fatigue, but also when you're at home communicating with family, when you're at school or you're at a conference like this, you might not be able to concentrate, you might get irritable, and so this has a wide-ranging effect. So the question becomes, why don't people just replenish their electrolytes? Well, it seems easy enough to do, but honestly, it's not always as simple as it should be. And that's because when you're faced with replenishment, you have a wide variety of products. So in this paper, we're focusing on sports drinks that claim they have great electrolyte values, right? But who's to know what the actual electrolyte content of these beverages are? You might be able to read the nutrition labels and place some blind trust that those are accurate, but the reality is a lot of these beverages, and when you mix them yourself from powdered varieties, the contents vary dramatically. And so how do we remove this blind trust? Well, current solutions use a multimeter method and alligator clips. The diagram on the bottom right shows how you can hook a multimeter up to a battery with alligator clips, hook that battery up to a container where you've placed some conductive edges, and then power on the battery, make sure you don't touch the conductive edges, measure the voltage, measure the current, get out some pen and paper or a calculator, calculate the current, the voltage, or use the current and the voltage to calculate the conductance, and then hopefully we can end up with an electrolyte value. This process is complicated to explain. It doesn't seem easy to use, and there's no guarantee that you're going to get reliable results. Who's to say that your working is going to be the same every time? In addition, this method suffers from hardware faults. If you touch the two ends of the container without having them placed in the electrolyte solution, the multimeter might just blow up. The fuse needs to be replaced, and so this is a costly and inconvenient procedure. The manual calculations are just not accessible to the masses as well, especially when you're traveling. So there needs to be a new sensor that can replace this multimeter method, and the new sensor needs to be easy to use. It needs to be able to compare and contrast the electrolyte contents of various beverages, and it should be adaptable so that we can embed it in everyday products like the water bottle in your backpack, your smoothie machine so you can make nutritious smoothies, or Gatorade tubs so that you're always consistently mixing the same level of Gatorade concentration. So we've done just that, and we have created Electrometer, the practical electrolyte sensor. And the sensor is discrete, it's easy to use, it removes the blind trust and guesswork, and it's accessible to everyone, no matter your expertise level. It operates on that same principle from the previous slide. We have a battery sending current along a circuit. The circuit is connected to an electrolyte drink and forms what we call an electrolyte bridge. But in this case, instead of measuring the voltage and the current manually, the current is going to reach the microcontroller. It's going to be an analog value. It'll be converted into a digital value and sent wirelessly to a smartphone. And the smartphone replaces the human having to do these calculations. It uses a simple voltage divider equation, so the model is not complex. It's just an equation. We calculate the resistance in ohms, and then we convert that ohms into resistance in Siemens. And this conductance can be used to infer the electrolyte value. We're measuring that current path along the R1 resistor on the bottom right diagram. This is the electrolyte bridge. The potentiometer resistor is what allows us to create that voltage divider. So the system is adaptable, it's easy to use. I won't read out all the text, but we have three main stages. First, you equip a container with our sensor, and then you pour a liquid into the container. The circuit is then complete. The current travels along from the battery through the liquid to the microcontroller. It's advertised to the smartphone. The smartphone calculates the electrolyte conductance and returns the results to the user. So it's super simple to use. We created a practical voltmeter design using an Arduino Uno and a potentiometer resistor. And in the example shown, we have an electrolyte bridge of a water bottle. This could be replaced by any everyday liquid container. We also have our communication circuit in the same sensor, which uses a Bluetooth module, which wirelessly transmits the data to a companion application, which has two screens. It has a sensor interface screen and a results analysis screen, where the user can interface with the sensor, but also see some electrolyte contents of whatever they're measuring. We created a prototype. It's not the prettiest prototype. It uses a breadboard and components that we have. And in future design iterations, this will be refined to embed in everyday objects. So in the demo on screen here, we can see when the sensors are disconnected, we have a 0 reading of voltage. When they're connected, you see 5 volts. These two prongs, the things I'm touching together, are what would be in that electrolyte solution and can be used to measure the electrolytes. Interestingly, if this was the multimeter method, the hardware would need to be replaced because the fuse would have blown by now. So we're resilient to hardware faults. We measured popular liquids like Gatorade and Powerade, sugar-full, sugar-free, powdered varieties, and we had a distilled water control, and we had 100% agreement between the multimeter and our electrometer sensor. So we're ready to use for application. If you're a user today and you want to ask our sensor, out of these two drinks, which one has more electrolytes? We will correctly be able to tell you which has more and by how much more does it have. Also, we have a better and improved ability to measure electrolytes on beverages with extremely similar values according to the ground truth multimeter method. One in particular that had an increased amount of potassium and sodium was said to have the same level across 2 drinks by the multimeter ground truth, and our sensor was correctly able to distinguish the two, whereas the multimeter method would leave the user confused and wouldn't allow them to choose the better option. We quantified the disagreement to investigate which beverages do we perform worse on, and it turns out the lower the concentration of electrolytes, the trickier it gets for our sensor to measure them in agreement with the ground truth. And we asked ourselves, why is this the case? And it turns out the multimeter method, when we're performing measurements, has a calibration option to calibrate it to different sensitivities. And so it can perform better on liquids like distilled water. So that we use this to motivate our future work, where we want to add ground truth methods with a scientific conductivity probe used in lab settings, but also with calibration liquids, which have known electrolyte values. And we want to perform a user study to be able to say what types of information would a user want to know about their electrolyte beverage. And then we want to actualize prototypes of our downstream sensor designs, which we also propose in the paper, that embed our sensor into an everyday product. These range from water bottles to high-value liquid containers like medicine bottles, to fruit probes for producers to see if the bananas and apples have consistent amount of electrolytes, but also in blenders. So when you're making smoothies or you're mixing drinks at home, you can have a consistent recipe guided by electrometer. Thank you for listening.
Thank you for the presentation. Our next presentation is the task as context prompting and for the accurate medical symptom coding using large language model. Let's welcome. Thank you.
All right. All right. Hi, everyone. My name is Cheng Yang. I'm from Stevens Institute of Technology, and today I will introduce our work task as context prompting for accurate medical symptom coding using large language model. So here's a brief outline of today's presentation. So first, I want to define what is symptom coding. It's a process of identifying clinical signals, signs, or complaints described in unstructured narratives, and then we map the extracted signals or like signs to the standardized codes. Okay. And so why do we care about symptom coding? The motivation, like we found, is that usually, like unstructured data, they come at the very first of the stage of the admission or like of the report. So we can find like the very first clinical signals before even the formal diagnosis, and this will give us an early warning system for emerging conditions. And by defining our own symptom set, we can tailor the label space to each study, and this will help us speed up our research and improve the real-time surveillance, and finally will create more accurate data for the analysis and in the field. So like some people will ask, like, what's the difference between ICD coding and symptom coding? So basically, ICD covers all range of medical codes. Symptom coding only focus on a narrower range, which can be defined by ourselves. It only focuses on the symptoms, but like ICD covers procedures and diagnosis. For input level, symptom coding would handle informal and subjective unstructured text instead of the more structured clinical notes or procedure reports for ICD coding. And for application-wise, symptom coding mainly focus on surveillance or trend analysis, and ICD coding is probably it's generally more focused on administrative tasks like reimbursement or billing. And we've summarized 3 challenges from previous works and current practices. And first is that existing research mainly focus on ICD coding, and which leaves the symptom coding such narrower task under-evaluated. And for traditional methods dealing with symptom coding, it just handle with 2 steps. First, extract the symptoms and then map them to the codes. But this will lead to a context loss. Sometimes the medical term can be ambiguous between each other. For example, stomach pain. You don't know if that's caused by the stomach or your abdominal outer pain. So the second point is this multi-stage of traditional method will require high computational power, and sometimes it'll make it hard to adapt to a new task. And finally, it's the common issue about data scarcity. So it's really hard to get clinical data in a large amount with well-annotated data set. So given these 3 challenges, our contributions can be the first is our task as context prompting, which we fold both steps, the extraction and the linking, into one LLM prompt. And we compare this with another prompt we made to mimic the traditional 2-step approach. And second, this one prompt, unified prompt workflow will help us improve the overall efficiency, scalability, and adaptability. And finally, we have provided a benchmark annotated data set, as well as a two-stage evaluation pipeline to help us evaluate the similar tasks. So the data set we use is called Vaccine Adverse Event Reporting System, which is, we call it VAERS. And the data we use is mainly 2 data, which is adverse event description, which is the unstructured report text, and the symptom list, which is predefined standardized codes based on MedDRA. And this can be this is shown on the figure on the right side. So for this work, we mainly focus on adverse event related symptom, just related to the vaccines only, which means we don't include any procedures or experiments in the data. So that's our self-defined scope. And for annotation and validation design, below, just make sure we have a solid and annotation process to get our test data set. And our test data set is called SimCoder data set. So out of 500 reports, which is the sample we get from the overall data set, we end up with 487 reports, and 13 of them were abandoned because of the ambiguous cases. And based on the frequency below, we can we derived the 2 sub-data sets from the full data set, which are SimCoder Common 50 and the Rare 50. So they are just basically targeting the top and rare 50 most frequently reported symptom. And based on the dataset statistics, most of the reports have less than 10 symptoms suggested. And for rare dataset, the reports tend to be longer than the common one. And then let's talk about our strategy, which is the task context prompting. So we kind of like derive this concept from our previous work. It's also called like text as context. So it generally just like a concept that we like the like kind of like the related annotation task. They kind of like guide each other for better accuracy and adaptability. And this will emphasize like how annotation tasks can help each other by sharing the contextual information. So instead of like we instruct the model to do like step-by-step instruction, we kind of like want to combine the whole text into like a more fluent but like a more contextual related sentence. And this will reduce the efficiencies which we've seen in traditional method, the two-step one. And we embed the context directly, so this will improve the adaptability across different domains, which will help us to transfer to other like similar tasks. And regarding to the symptom coding, this idea will help us to embed our specific instruction to the prompts to help define our study, and it will inspire our TICO framework to test how large language model generalize from ICD coding to symptom coding, while like enhancing the accuracy in both like linking the symptoms and like the as well as the original mention. So here's the general structure of our prompting. Basically, for clinical text part and the prompt body, they're basically the same. So for clinical text, it just contains the original report text. And for the prompt body, it just contains the common instruction to the model. What really matters is the prompt header, which we designed another prompt called TASI, which this prompt kind of like mimic the traditional two-step approach. So like we can see like we first ask the model to extract the symptoms and then ask it to map it to the standard codes. However, in TACO, which is the orange font, we kind of like combine this two sentence into like shorter, concise sentence, and as well like in the output instruction, it's gonna be different because we ask the model to generate two results for the traditional method because it's a two-step process, and we only expect one result from the our TACO method. So to evaluate our output, we have like a two-stage evaluation pipeline. We like in the first stage, we want to make sure like all interested symptoms codes are being extracted. While like in the second phase, we try to like compare the original mention from the data input for each corresponding symptoms to make sure that we have linked them to the correct codes. And this is like a general framework of our TACO prompting, which we have already covered each section previously. And so the overall performance, we observed that GPT-4o and GPT-4 Turbo basically outperforms all the models, and which showing the trend that with better model you can have like better performance no matter like what prompt strategy you have. So like in order to like investigate the impact of our prompt, we find that like our TACO prompting just generally like outperform across all metrics than the TASI, which is the traditional one. And we also investigate the common and rare cases, and we kind of like run the same experiments on both of them, and we we kind of like find that like models are generally like perform like the overall performance kind of like align with our previous solution, that with like more powerful model it will just get better results. But like for model kind of like generally underperform on rare cases because there are like not enough rare data in the field, and also like for the previous like prompt variation, we can also observe that the taco is generally perform better overall than the TAC, which is the traditional one in this diagram. So finally, I wanna just due to the time constraint, I just wanna include one error analysis. So we kind of like try to understand the model output discrepancy. So we compare all the model outputs with our labels on the single example we choose, and the model are like having trouble identify some symptoms like rash macular, and the extraction accuracy becomes better as the model capacity grows. So here's a summary. So we have shown that TACO, which is our strategy, outperforms traditional methods on symptom coding task from accuracy, robustness, and adaptability. And we created a valuable dataset called SimCoder to provide a benchmark for their study. And we designed the systematic evaluation pipeline for both the extraction and the linking process, which can be leveraged on further similar tasks. Yeah, thanks to my team and the funding support. Thank you all for listening.
Thank you for the presentation. Thank you again. Our next presentation is HALO, the hallucination analysis and learning optimization to empower LLMs with retrieval augmented context for the guided clinical decision making. Thank you.
Hello everyone. I'm Sumeera Anjum. I'm a master's student from University of North Texas, and I'll be starting my PhD next fall. I'm here to present my work, Hallucination Analysis and Large Learning Optimization. This work is done in collaboration with my PhD colleague Hangzi, Dr. Zhao, Dr. Jinpek, and Dr. Xiaoping from University of Tennessee, and under the guidance of my mentor and advisor, Dr. Yunhe Feng. Yeah, so these days, large language models are revolutionizing many tasks, but they have a persistent problem called hallucinations. These are the instances where the models generate incorrect or fabricated answers. In healthcare domain, these are not just unsafe and unacceptable, but can be very dangerous, as they can lead to misdiagnosis, unsafe treatment recommendations, and compromise the patient's safety as well. The second major issue is large language models, which are trained on static data sets, can easily become outdated. Our project, HALO, addresses both these problems by grounding the large language model's responses in updated and reliable sources. Our proposed solution is a threefold framework, where first comes the multi-query generation, in which we generate multiple semantically diverse reformulations of the single query to broaden the retrieval coverage, after which we get the documents and re-rank them using maximum marginal relevance. After which, the final step comes prompt engineering, where we create prompts using few short examples and chain of thought reasoning template to guide the model for stepwise and factual answers. Our objectives with this framework is to improve the correctness of our LLMs to medical question answering tasks and maintain this improvement across diverse medical subjects and demonstrate this performance for various commercial and open source LLMs of different sizes. Here, this slide shows the framework where the first component is multi-query generation, in which we start with a single query and generate multiple formulations. These formulations are then passed to the contextual integration system, where the documents are pulled and the embeddings are created, after which these are re-ranked using maximum marginal relevance. Finally, we get to the prompt engineering, where the prompt is constructed using the original question, the re-ranked context, and few short examples along with the chain of thought reasoning template. These all are given to the LLM to generate the final output. First step, multi-query generation, in which we create diverse formulations, is fundamentally important because this enhances the retrieval, after which this is done through LangChain's multi-query retrieval module backed by an LLM. This helps the model to explore the different angles and structure and terminology of the original task by generating different formulations. These formulations are used to retrieve the context from an external source PubMed, after which these embeddings are generated using Hugging Face Instruct Excel model. Finally, re-ranking is done using maximum marginal relevance. This mathematical formulation considers both how relevant the original question is to the retrieved document and how different the document is from the already retrieved set of documents. This is done iteratively, and the lambda fine-tuning is done to balance the relevance and novelty of the obtained documents. In few short prompting, we include few curated question-answer pairs in the prompt, which mirror the style, structure, and terminology of the original task. This is done to reduce the variance and randomness of the LLM's output, after which the chain of thought template is given. This instructs the model to go through step-by-step reasoning rather than directly jumping to the answer. This is the template which we have used. This is the example framework of the one of the question from the MedMCQA dataset. On the left side, we can see the original question, how the LLM alone itself gives the incorrect answer, but upon integrating the Halo framework to the LLM, generates the correct answer. Coming to the experimental setup, we have used MedMCQA dataset with 194K diverse questions of 21 subjects. And the model is, these models are tested, ChatGPT 3.5, Llama 3.1, and Mistral 7B. The retrieval source for us was PubMed, which is a comprehensive database with 35 million plus peer-reviewed articles. Coming to the results, on the left we can see that the BERT models, which are trained and fine-tuned on medical data sets, have achieved the highest accuracy of 60%, which is comparatively low. Coming to the right side, where the LLMs have achieved higher accuracy than 60%. First, on the top, it is just the LLM without the Halo framework, and below we can see after integrating Halo framework, the accuracy has improved consistently without fine-tuning here. To thoroughly evaluate our framework, we have performed subject-wise evaluation on each of the LLMs. First is ChatGPT 3.5, and here we have grouped the accuracy with and without for each of the diverse subjects. These subjects range from core clinical concept medical subjects to preclinical sciences and specializations as well. So the improvement of our Halo framework has been shown in all of the three LLMs. This shows that our framework is consistent across different LLMs, and although it is open source or commercial LLM, the performance has been increased, and it does not also depend upon the size of what the LLM is used. Coming to the ablation study. So here we can see that upon only using the prompting techniques, we can see a slight boost in accuracy of the LLMs, but our framework, Halo, upon integrating the multi-query generation, the retrieval framework, and the prompting techniques, has consistently improved across all of the LLMs. So the key takeaways for our framework are our Halo framework integrates RAG, maximum marginal relevance re-ranking, and prompting techniques to improve the framework without needing for fine-tuning of the LLMs, and can work on different diverse subjects and LLMs, although even if they are commercial, open source, or of different sizes. And our work is open source and can be easily accessible and adaptable to different domains. Thank you.
Thank you for the presentation. Our next presentation is Explainable Feature Engineering in Health Data Science, empirical comparison of ChatGPT 4.0 and classical machine learning method. Let's welcome.
Hello, everyone. I'm Nick, and today I'm going to be presenting our paper on behalf of our co-authors, Explainable Feature Engineering in Health Data Science. So feature selection is a critical part of any healthcare ML pipeline, and it directly affects both model performance and interpretability, which is crucial for clinical acceptance. Traditional feature selection methods are highly effective, but operate purely on data statistics and don't consider the broader clinical impact. In contrast, large language models like ChatGPT are pre-trained on extensive text and have implicit knowledge that could inform feature selections in clinically meaningful ways. So from this, our goal is to evaluate whether ChatGPT 4.0 can serve as the useful tool for feature selection and compare it to the output established by popular ML methods. For this, we had two research questions. The first question was, can ChatGPT 4.0 serve as an effective method for feature selection comparable to classical ML-based feature selection techniques such as information gain, correlation-based feature selection, and principal components analysis? And does ChatGPT 4.0 rely on its pre-trained knowledge to identify and select important features? From this, we focused on clinical significance and the technical significance. Clinically, from a clinical perspective, we focused on the crucial step of feature selection and feature importance, aiming to enhance the applicability of ML models in a healthcare setting, as poorly chosen features can undermine clinical confidence and regulatory approval. And from a technical perspective, this is one of the first empirical studies evaluating ChatGPT 4.0 as a feature selection tool for structured clinical data and under anonymization, simulating privacy-preserving ML settings where feature names may not be shared with external models. For this, we used two data sets. The first is SEER, which is a cancer survivability prediction data set from the years 2004 to 2013, where we focused on bladder, kidney, pancreas, and prostate. And we used NESQIP from 2016 to 2020, which predicted 30-day unplanned reoperation following shoulder arthroplasty. And both data sets contain clinical, demographic, and outcome variables. So this is our pipeline. The first step we did for both data sets is pre-processing, where we discrete continuous variables and perform feature anonymization. For anonymization, we replace feature names with generic codes such as F1 and F2 to test ChatGPT's reliance on feature names. We then perform two stages of feature selection. The first is classical feature selection. We applied information gain, correlation-based feature selection, and principal components analysis to represent both univariate, multivariate, and dimensionality reduction methods. And for ChatGPT 4.0, we used instruction prompting. The model was provided with a table of features, and the prediction task was asked to rank by feature importance. And we focused on feature importance because it aligns well with the nature of our tasks, so it can be prompted to focus on specific features. After that, we evaluate our feature sets from the selected methods with experts. We had 3 health experts and 2 data science experts evaluate our results. So these are the results for the classical machine learning approach. From this, across both data sets, classical ML methods produce consistent results. And for SEER, features like age, tumor size, summary stage, extension, and lymph nodes were consistently identified across all methods. For NESQIP, the classical methods identified BMI, age, diabetes, smoking, and steroid as the top predictors for reoperation, and all these selections aligned closely with established clinical knowledge for both oncology and surgical outcomes. For ChatGPT 4.0, it also identified many of the clinically important features. In SEER, ChatGPT was selected many key features, including summary stage, lymph nodes, and extension, but there is some variability when we introduce anonymization, which suggests partial reliance on feature names for more complex data sets. For the NESQIP dataset, ChatGPT was highly consistent, even when the features were anonymized, repeatedly selecting BMI, age, diabetes, and smoking as the important predictors. So as I mentioned, we had a panel of 3 healthcare professionals and 2 health data scientists independently review the selected features. For SEER, 7 of the 9 features selected were 7 of the 9 features selected by classical ML methods were also unanimously selected by all domain experts. And ChatGPT 4.0 largely aligned with expert selections for primary features, but showed more variability on second and marginal features. In the NESQIP, both classical ML methods and ChatGPT 4.0 demonstrated very high agreement with expert review and achieved 80 to 100% concordance among most of the top-ranked features. And this further supports that ChatGPT 4.0 performs very well on datasets with strong statistical signals and more straightforward features. So in conclusion, ChatGPT 4.0 demonstrates potential in identifying key features for healthcare datasets. It exhibits variability and limitations in feature ranking, and is not ready as a standalone feature selection tool. ChatGPT 4.0 primarily relies on data-driven patterns for feature selection, and it focuses on the intrinsical statistical relationships and structural properties. It is more reliable for well-structured datasets like NESQIP, and has more variability in complex datasets like SEER. The effectiveness of ChatGPT 4.0's feature selection is influenced by the characteristics of a dataset, and it shows the importance of tailoring it to applications for specific data contexts. So moving forward, there's a couple limitations that we noticed. First is the variability of ChatGPT's performance across the datasets and experimental conditions. And the second is that expert reviews may introduce subjectivity in assessing feature relevance, as some experts may pick features that are more important to them rather than just a specific study. And then for future work, we're planning on benchmarking with other LLMs. Right now, we only focus on ChatGPT 4.0, but we're planning on extending it to Llama and Mixtral. And we also want to explore hybrid models that combine statistical and LLM reasoning and evaluate more quantitative evaluation frameworks. Thank you.
Thank you for the presentation. Our last presentation is heterogeneous sensing-based indoor localization leveraging Bayesian prior estimation. Thank you.
Hello everyone, my name is Chaemin Lee. I'm from Rutgers University. So today I'm glad to present our work, heterogeneous sensing based indoor localization using leveraging Bayesian prior estimation. This is a joint work with my advisor, Professor Ying Chen from Rutgers University, Professor Cong Shi from New Jersey Institutions of Technology, David Melf, and Jerome Henry from Cisco Systems. Indoor localization plays basically a central role in the smart healthcare applications, and such as patient monitoring, outdoor fault detections, and also daily health tracking. These applications are often performed in the areas such as patient's house, clinics, or long-term care facilities, where the key real-time knowledge of the locations of the patients or the persons is essential for their safety and also for the facility's responsibility. But due to the poor performances of GPS in indoor scenarios, these wireless-based indoor localizations often attract a lot of attentions. And these techniques often offers a promising alternative for pinpointing user locations using Bluetooth or Wi-Fi inside a building. Existing wireless-based localizations can be distributed into 2 categories. Well, first is the range-based localizations. Well, they basically estimates the user's locations using triangulations, giving the estimated distance and also over the angles between the users and the devices. However, such methods is often susceptible to the change of the environments, basically such as multipath reflections, interference from the environments, which ultimately degrades the distance and also angle estimations. Furthermore, the angle-based triangulations, as an example, it also usually requires line of sight applications when they're being used. And furthermore, it often requires complex hardware, such as phase array radar, which is hard to deploy and inefficient to deploy in the real-world applications. Another type of methods is more efficient, but it's called range-free localizations, which is basically profiling the signal characteristics, such as magnitude or the phase of the signal, and from these known locations, which basically store them as a fingerprint, as a database. But however, such methods also susceptible to the change of the environments and also to the signal fluctuations over time, which will cause mismatching between the newly observed measurements to the fingerprints that are pre-stored in the system. Therefore, such methods often require frequent recalibrations of the profile fingerprints. So therefore, it's inefficient to deploy it in real-world applications. So to overcome the challenge of the signal variations using the fingerprinting, our key idea is to leverage the heterogeneous sensing, specifically by fusing the Wi-Fi CSI and also the Bluetooth RSSI signal within a Bayesian inference framework. By combining these two modalities, we aim to construct a joint signal statistical prior that is both discriminative and also robust to environmental changes. Before we directly dive into the system design, we wanted to understand how the different wireless modalities respond to the environmental changes. So therefore, we conduct a preliminary experiments in the indoor space where we collect both the Bluetooth RSSI and also Wi-Fi CSI before and after we introducing changes to the environments. Well, as you can see from the figure, which demonstrating the heat maps of the RSSI values. Some areas we're having the weak, strong RSSI values will become weaker after we change the environments, and this happens vice versa. Similar things happen to the Wi-Fi CSI, but to be more specific, to be more detailed, and to be more well represented, we actually plot the CSI in the 2D space using the TSNE methods. Therefore, you can see that two clusters that before and after we change the environment, the CSI data itself shows significant separations. Therefore, the environmental changes certainly impacts the data itself, not just the Wi-Fi, but also the Bluetooth. In order to build a robust, heterogeneous sensing system, so that we require to address the three key challenges. Well, first, as I said before, the spatial and temporal variations itself can distort the fingerprinting of the CSI and RSSI. Therefore, we need to design methods that to align the multi-model prior during the online inference phase to the prior from the offline training phase, so that the trained CSI and RSSI fingerprints can be adapted for localizations in the inference phase. And second, during the offline training phase, the multi-model prior needs to be incorporated into the building fingerprints. Therefore, which means that this prior need to be adjustable. However, currently, it's difficult to build such a adjustable prior, as the conventional machine learning models, they are usually fixed their parameters after the training. And third, we have the noisy measurements is also another problem, which will introduce by interference or hardware imperfections from or fluctuations from the environments. Therefore, we need to adapt some signal pre-processing methods to filter out the noise and to ensure the reliability of the signal features. Therefore, our system is demonstrated as follows. Once we acquire the Wi-Fi CSI and also Bluetooth RSSI, we first implement a signal pre-processing pipeline designed to enhance the signal reliability for each modality. And during the offline training phase, we design multi-model prior estimations to capture the environmental conditions in Wi-Fi CSI and the Bluetooth RSSI as the covariance matrix representations, which we use as a prior. And then based on this prior, we integrated it into our loss functions that can minimize the mapping between the features and the physical locations, which we adapted to the new environmental conditions. And in the online training phase, we design adaptive localization methods, matching methods, which we can replace the multi-model prior in the training CNN to a newly estimated prior. To be short about the technique, for the signal preprocessing for the RSSI, we're basically just utilizing moving average and also outlier removal methods through the sliding window to smooth the RSSI data, acquiring a reliable measurements. And for the similar things happen to this Wi-Fi CSI, where we apply filtering, low-pass filtering, and also phase unwrapping techniques to having continuous measurements in the CSI amplitude and also the phase. But to be specific about our techniques for the multi-model prior, we first modeling the Wi-Fi CSI and the Bluetooth RSSI as the mapping functions, which reflects the transformations from the signal magnitude to the estimated positions. And based on these mapping functions, we derive a Gaussian prior distributions based on its sensing vector, which includes such a mapping functions. And as you can see from these equations, we have a sigma variables, which indicates the covariance matrices specifically to each of the modalities. And to incorporate the multi-modalities, we fuse the priors of the CSI and RSSI into a joint distributions as shown in the probability as shown in the bottom. Similar to, besides the prior, we also calculate the likelihood of the probability, which is indicated in using these equations, which we calculated by using the training data using the prior. And then we need to integrate both the likelihood and the prior into cross entropy functions, loss functions for CNN optimizations, as you can see from this equation. Once we train the CNN using such a loss, then move on to the online matching phase, where we need to adapt the system to a new environmental conditions using the refined prior estimations. Therefore, we start the prior refinements by comparing the incoming new data with the base prior. And then we updated the prior's covariance matrices based on the newly observations. And then, once the prior is refined, we then performs the CNN-based inference using such a prior, using the same model trained during offline. And the predictions is shown as below. Based on such a system, we also need to evaluate its feasibility. Therefore, we conducted experiments using USRP devices, which operated in Wi-Fi and also Bluetooth frequencies separately. We also, for the specific data collections, we also built such a test bed, which includes 45 known fingerprinting locations in the apartments. And to simulate the environmental variations, both in spatial and also temporally, we arrange the furniture placements to alter the multipath, and also we ensure enough time gapping between the training and also testing data collection. To be short, these extensive experiments actually demonstrating the effectiveness of our system and also the robustness of our system. Whereas you can see from these figures, the Bayesian CNN model, which applies our Bayesian framework, keeps the localization accuracy around 80%, while the other models, such as machine learning models or the regular CNN models, will actually suffers greatly by facing the environmental changes. Furthermore, our Bayesian CNN model actually possesses the lowest medium error rates of the 0.72 meters comparing with other baseline models. To conclude, we propose a multi-model indoor localization using the Bayesian prior estimation approach to mitigate nonlinearity. We also design a prior control technique for deriving prior distributions for each sensor modality. We also designed a model optimization to contribute to better model convergence when facing data in prior representation. And we also built a wireless testbed to show the heterogeneous wireless systems effectiveness based on various environmental conditions and variations. Thank you for your listening.